Alright, we're going to finish up this chapter of geometry by looking at three-dimensional figures. We'll mostly be doing problems where we need to find either the volume of a three-dimensional figure or maybe the surface area. So a couple of notes here. V, capital V denotes the volume. That seems pretty straightforward. But there's different kinds of areas of these figures. So capital A always denotes the total surface area. S denotes the lateral surface area. So lateral surface area means not including the bases, like the area around the sides. So there's a difference between A and capital S. Capital B, this one is we want to take note of. Capital B denotes the area of the base. All right, so little b in a lot of formulas denoted like a length of a base side. Capital B denotes the area of an actual base of a three-dimensional figure. And P, little p, denotes the perimeter of the base in these formulas. So again, there's not much need to memorize these formulas, but we just need to be able to pick out the formulas that we need when we need them. So I'm going to take just a couple of minutes to talk about these. I'm going to first just say there's some similarity between, I'm going to take, say, the rectangular solid, the right prism, and the right circular cylinder. There's a similarity to these figures and how we find their volumes. All right. Notice they're all figures where we have some base. The base is either a rectangle or a circle or whatever shape. That right prism, I drew the base there so that the base was a hexagon, but it works for any shape base. So we take some base and we raise it up to a uniform height. So notice that the top is flat. It doesn't come to a point. The top is flat. And whenever we find the volume of a figure like that, we find it by taking the area of the base and multiplying it by the height. In the rectangular solid, in the box, that's length times width times height. Like, we're probably used to knowing that formula, length times width times height, but it does adhere to that basic idea that we take the area of the base and multiply it by the height. In fact, for the right prism, that's exactly how we write the formula, because how we find the area of the base changes depending on what the base looks like. So we just write it as area of the base times the height. And for the right circular cylinder, well, that base is a circle, and we know that a circle has an area of pi r squared, so the volume is pi r squared h. Now, I'm going to compare next the regular pyramid and the right circular cone. The regular pyramid, you take any base. Here I've drawn that base as as a rectangle, or maybe even it looks a little bit square, but the base could be anything. It could be a hexagon, it could be a triangle. But this time, instead of raising it all up to a uniform height and getting a flat top like we do with the right prism, what I'm doing is raising it up to a point. And just note that the formulas are really similar. But when I raise it to a point instead of a uniform height, the volume is 1/3 of that prism. The same thing happens if we compare the right circular cone with the right circular cylinder. So instead of raising it up to a uniform height, like with a flat top, I'm raising it to a single point, and these volume formulas compare in that way. We have the cone is 1/3 of the volume of the cylinder that has the same height. The sphere, this one is easy to kind of recognize, I think, in a formula. First of all, any formula that has pi in it has to involve something with a circle. So a cylinder, a cone, or a sphere. But the sphere is the only figure we have that is completely determined by one measurement, by one dimension. We just know the radius, and the sphere is all these points that are the same distance from the center. So that's why the volume, we only need to know the radius. In the other ones here that involve pi, of course, we need to also know the height. Similar with the area of a sphere, again, we only need to know one measurement. It's the radius. So I'm not going to talk too much more about these formulas here, but just know that you can refer to the sheet when you need it as you're working on exercises. It's a good idea to be able to pick out the formulas you need. even if they aren't identified for you. Let's begin by finding the volume and surface area of this cone. So it's a cone, so I'm going to go to that page. I'm going to pick out the formulas I need. For a cone, the volume is 1/3 pi r squared h. And we have the measurements that we need, right? They gave us basically everything we need to get the volume. So 1/3 pi times 8.2 centimeters squared times the height of 10 centimeters. Now think about this for a moment. Think about what the units ought to be. We're taking centimeters squared that we get from r squared and multiplying it by centimeters. So we're going to get centimeters cubed or cubic centimeters as a result. 1/3 pi times, and I'm going to just do this calculation in the calculator here. So 8.2 squared times 10. And that's 672.4. And this is cubic centimeters. And then, let's see, in terms of pi, I'm going to take the 672.4 and multiply it by 1/3 or divide by 3. And that's 224.133. So in terms of pi, that's what we have, 224.133 pi, and then we can approximate, and really I did round that coefficient there, so I'm going to call that approximate as well. Multiply by pi, and we get 704.14. Right, so there's the volume. The next thing we want is the surface area. So for the surface area of a cone, we have these two formulas. Remember, capital S is just the lateral surface area. If they don't specify, when they ask you to find the surface area, they really mean the total surface area. So there's two parts to this, and the lateral surface area is always part of the total surface area. So we get the total surface area by taking that lateral surface area, pi rs, and adding pi r squared. We could tell where the pi r squared comes from, right? The base of this is a circle, so the surface area has to include that. That means that the pi rs, that's this area like around, and we need little s, that's the slant height here, okay? So when you're finding the slant height, note that there's sort of a right triangle embedded with one of the legs is the height, the other leg is the radius, and s is the hypotenuse. So let's see, I'm going to write down this formula and then we'll work on finding s. So this is pi r squared plus pi rs. So we know, so here's s. Again, I'm just going to kind of highlight this, or this right triangle that we have. We know that s squared is equal to 10 squared plus 8.2 squared. And then we could take the square root. And we get, probably have to approximate this. So 10 squared plus 8.2 squared gives us 12.93. And that'll be centimeters. It's a length. So now let's plug this stuff in. Pi times 8.2 centimeters squared plus pi times 8.2 centimeters times 12.93 centimeters. Now, take a look at this. Think of the units that we're going to end up with. Think of the units we should end up with and see that that's exactly what happens. Our first term will have centimeters squared, and we're adding that to another term that's also centimeters squared because we have centimeters times centimeters. So 8.2 squared, that's 67.24 pi. And then 8.2 times 12.93, oops, is 106.026 pi. These are both square centimeters. So in terms of pi, we can get that first. So 106.026 plus 67.24, that gives us 173.266 pi. Square centimeters, and then we can approximate. Times pi. 544.33 square centimeters. All right, one more example to go here. We're going to find the volume and surface area of this figure. We have a cylinder surmounted by a hemisphere, so it looks like kind of like a silo or something. So let's start with the volume. We know for the volume, we're going to take, we're going to get that by adding the volumes of the two components here. So the volume of the cylinder plus, and we have a hemisphere, so that's half a sphere. So I'm going to write that as half the volume of a sphere. The volume of a cylinder is pi r squared h. The volume of a sphere is 4/3 pi r cubed, so I'm going to have half times 4/3 pi r cubed. We can simplify this. The 2 will cancel into the 4. So now let's start plugging things in. We know the radius is 35 feet. Times, now we need the height, but they gave us the total height from the bottom to the very top of the hemisphere. We need this height. So that's the height of the actual cylinder. And the way we could find it is just realize that if I start at the top of the cylinder part, going upward, that's a radius, right? That's the radius of that hemisphere, so we know that that's 35.0 feet. So we're going to find that height by taking 112 minus 35, and that gives us 77 feet. And now, let's see, moving on to this hemisphere, we have 2/3 times pi times 35.0 feet cubed. So let's see, if we get this in terms of pi first, this first calculation, I'm going to take 35 squared times 77. And that's 94,325. So 94,325 pi. And the units were going to be cubic feet. We have feet squared times feet. So that's cubic feet. And this, for the hemisphere part, I'm going to have 35 cubed times 2/3. And that is 28,583.333. I could approximate like that. I could also just write it as a fraction if I want to actually get an exact value. If you know that something can be expressed as a fraction, you can get your calculator to convert a decimal to a fraction. You hit the math button. The very first option is an arrow frac, so that means convert this to a fraction. And then hit enter. And there it is as a fraction. If you do that and it just gives you the decimal right back, it's probably because it's likely that the value you started out with is irrational and can't be written as a fraction. But here we have the nice fraction, 85,750 over 3. And of course, if you wanted to just use the decimal that we found, that's fine too. We can get an exact volume. So I'm going to take the 94,325, add that to 85,750 thirds, and that'll be my factor in front of pi, my constant factor in front of pi, plus 94,325. And that's 368,725 thirds pi, and that's how many cubic feet we have. And then of course I'm going to go ahead and approximate this. And we get 386,127.92. Alright, so that's the first phase of this problem is done. They asked us to find the volume, so that's done. Next, let's find the surface area. So this surface area, we have to kind of think about what's the surface of this figure. So if it were just the cylinder alone, we'd have the top circle, or the bottom circle base, and the top circle as part of the area. But this top circle right here, that I'm kind of highlighting or shading in green, that's not a part of that's not on the surface anymore because there's a hemisphere on top of it. So when we put together this this surface area, you know, we need to grab the cylinder part and half the area of a sphere. But for that cylinder part, we're going to just have one base and then the lateral surface area. So that one base is just pi r squared. The area around that lateral surface area, that is 2 pi r h. So notice, I'm just going to kind of scroll back up here. If you look at the surface area, the total surface area formula for a cylinder, they have 2 pi r squared. That's because they are including that top. But we don't have that in our figure. So we have just 1 pi r squared. And then half the surface area of a sphere, so that's 1/2 of 4 pi r squared. And I think we have everything we need to plug in, so let's go ahead and do it. Pi times 35 feet squared plus 2 pi times 35 feet times 77 feet plus, now for the sphere, 1/2 of 4 is obviously 2 pi r squared, 35 feet squared. Okay, so let's start at the beginning. 35 squared is 1225. So 1225 pi, 2 pi times, well, let's see, I'm going to do 35 times 77 times 2, and then just attach the factor of pi on the end. And that's 5,390. Pi. And then 35 squared times 2 is 2450 pi. And these are all square feet. So we can get a nice exact value in terms of pi. So 1225 plus 5390 plus 2450. Is 9,065 pi square feet, and let's approximate. 28,478.54. All right.